Let us continue with this example. We are given x1, x2, x3 that belongs to R4 space. These three vectors are obviously independent. They cannot be formed by linear combinations of the other two. So they are independent and they are basis for a subspace because we need actually 4 of them to span R4, the whole space of R4. Since we are only given 3 of them, then only a subspace of R4 can be constructed using these 3 independent vectors. What we want now to create is an orthogonal basis, because it is obvious also that x1 and x2 are not orthogonal with each other, as well as x3. To do that, we would use the Gram-Schmidt process. Remember the Gram-Schmidt process? To create the first vector is trivial. We let v1 to be equals to x1. Therefore, the span of x1 is the span of v1 since they are the same vectors. We use the notation w underscore small subscript 1 to denote one column vectors in W. Now, what about x2? To construct the second vector v2, v2 must be orthogonal to v1. So we use this equation. This equation is v2 is it is constructed by x2 minus the projection of x2 on w1. Remember, w1 has only one vector now, which is v1. What is this equation? As a refresher, you can see chapter 6.2.5 for the explanation of this equation, projection of x2 onto a subspace. If you are back, then we have x2 here. What is this? This is a constant multiplying by a vector v1. So let's see, where is v1? So this is v1. This is v2. Sorry, this is x2. So this is x2 minus, and this constant is this guy. This vector here is the closest point along v1 to x2. Answer is here. This vector is equals to v2. v2 is orthogonal to v1. You can try to do the dot product of this. And this v2 and v1 spans the same space as x1 and x2. You can then continue to calculate projection of x3 onto w2, and then you can get v3. Please try to do this yourself at home and check that your answer is the same as what we have in the slide. You'll notice something here. v1 and v2s are the orthogonal vectors. Wouldn't it be very nice if v1 dotting with v1 equals to 1 and v2 dotting with v2 equals to 1? And if this is so, this reduces and we have the octonormal decomposition instead of orthogonal decomposition. So how do we get the length of v1 and v2s to be equals to 1? In the next slide, we'll show you how to how to form an octonormal basis from an orthogonal basis.